Hello, can y'all hear and see me? Um, okay, cool. Let's see, so is this, okay, that's how I share my screen. Hello. So I guess, yeah, I'll just wait a couple minutes and get started. I do, yeah. I think I know how to share them just by doing this. Just, yeah, looks like that's working. Cool. So y'all can still see me while I'm sharing my screen, right? Cool.
Hello there.
Hi.
Is everything all right? You need help setting up anything?
Um, I think I got it. Yeah.
Okay,
Um,
cool.
my screen's being shared and everything, right?
Yeah, I can see everything fine.
Sweet.
All right, awesome.
Okay. Yeah. So I mean, just if you have questions, I have the chat pulled up, so feel free to ask while I'm going. I don't know. Is there a way to for I guess the sound will let me know that someone messaged something. So um, yeah, definitely feel free to stop me at any point. Um, yeah. And yeah, I guess we can go ahead and get started. So just to kind of introduce myself, my name is David Rein. I am a ML research engineer at a startup based out of Toronto called Cohere. We do natural language processing. Basically, we train large transformers to solve general kind of NLP tasks. I'm still a student, but I'm taking some time off. So I have one semester left, and I'll finish that up next year sometime. But yeah, so I think we can just kind of get into it. Um, okay, so first off, what is this workshop and what isn't this workshop? Um, so uh, in this workshop, I will kind of go through just the main ideas behind language modeling. I'll talk about a couple of the most important language models that people use, the ones that kind of work the best. I'm going to go through this NLP framework called Hugging Face that is really, really useful. Yeah, I mean, my goal, what I hope from this is that you kind of have the foundation upon which you can kind of make some application that uses like a deep learning model to do something with text. So that's kind of my goal. I'm not going to go through the history of NLP. There's just not enough time for me to do that. I'm also not going to talk about how to deploy these models, which probably would be pretty useful, but I just don't have any experience doing that, so I couldn't give good advice. And the other thing is that this isn't going to really involve much math or any math. That's not to say that the math kind of underlying these models isn't important and that you shouldn't learn it. It's just that I don't know kind of where people are, what people's backgrounds are. And so in order to make this accessible without, spending the whole time on just like a couple things, I can't really, I have to kind of keep it somewhat high level. So yeah, that is what we'll be going through. And yeah, let's get started. So language modeling, what is it and why should you care? So the core idea behind language modeling is we're going to look at language from a statistical perspective. So a lot of linguistics, starting from I guess like the 40s and 50s, took a very kind of formal approach to language. So this is kind of like the Chomsky style of linguistics, where you try and just like rigorously and precisely figure out the kind of formal rules and the logic behind syntax and semantics and how those kind of combine to create meaning and let us communicate. This is a different view. This is basically the view where language is a set or a series of characters or words, and there's some kind of underlying probability distribution that describes or prescribes what those characters or words will be. And language models try to figure out this distribution. They try to create a model for it, and we'll talk about what that actually means. But yeah, that's kind of the goal. The current best way of doing this that we have is by training large neural networks on just a ton of data. So usually we like scrape it from the internet. A lot of popular language models have been trained on all of Wikipedia or a large number of digitized books, things like that. And yeah, why should you care about this? Well, I think the main reason is that it's just currently the best method or known way we have of getting our computers to just understand language. So just a couple months ago, Google posted in some blog post that they use BERT, which is one of the language models we're going to be talking about. They use it in almost every single Google search, and there are just a ton of different kinds of things that you might want your computer to do with language. There's certainly many things that involve text data that you don't need language models for, right? So you have some input on your website where you want users to put in their email address and you want to make sure it's like properly formatted, right? You don't need a language model for that because there's just a very specific kind of rule or set of a couple rules that we understand and can define to check and see if the email is valid. Language models let you do things with language that you can't take this kind of formal like super specific approach where you define several rules to solve it. So this is things like you want to summarize some large amount of text, right? We don't. I can't think of or describe like a precise way to do that for any kind of given general text. So you need some kind of language model to do that. But yeah, I mean there are a ton of other things that you can do. Things like style transfer, like if you want to read some or change the style of some writing to be in the style of some other author. Just language generation, which we'll talk about. Semantic search, as Google is doing, and plenty of other things. Yeah, are there any questions about kind of why language modeling is interesting or important? Yeah, and also, of course, yeah, feel free to just send a message in the chat at any point in this if you have a question. Okay, so yeah, how do we get started doing this? So the first step is called tokenization. Tokenization is basically where we take either bytes or characters and we convert them to a sequence of integers, basically. We call these tokens. So why do we do this? Well, one part of it is just so that we have a numerical representation of text, just so that your computer can understand it. You might ask then, why don't we just use the bytes, the raw bytes that form, the ASCII text or whatever? So I kind of pithily put, a word is more than the sum of its parts. But what I mean by that is that, a word is formed of characters. Let's say that we just we're just using a single token for each character. So let's say we're just kind of focusing on like English, and so we have 26 tokens, and these tokens form words, right? Each word has a very, or a relatively specific meaning that it captures, and you kind of lose a lot of information by just representing words as individual tokens. One kind of example of this is this first bullet point here. So some tokenizers allow multiple words to be a single token. So for this example, you can imagine the phrase New York, right? The phrase New York has a much more specific meaning than the words New and York just kind of by themselves, right? New York is like its own entity, basically. And so with tokenization, you can learn specific kind of entities that show up often. So New York shows up often, and so a good tokenizer would represent New York as a single token. And then your model, when it sees New York, it doesn't have to do kind of internal processing to figure out that you're talking about, this entity New York, as opposed to like just these separate things, New and York. It can just see the token for New York and be like, oh, okay, this is that token, and this is what is being referred to. But yeah, so some tokenizers operate differently, and yeah, it's the kind of benefit of tokenizers is that you can flexibly, take in text that you haven't seen before, and that you can represent misspelled words really easily. So yeah, is Dialogflow the main NLP division at Google? I don't. So I'm not super familiar with Dialogflow. I've heard of it. I wouldn't characterize it as the main NLP division. I think Dialogflow is kind of a product that Google services for creating kind of chatbots and that kind of thing. But I think there's a large amount of NLP research at Google broadly. Okay, So we have tokenization. So now we have kind of a series of tokens. But going back to language modeling, I said language models model the probability distribution over tokens. But yeah, I didn't really explain what that meant. So I think this is kind of best explained through a couple examples. So in this first example, we have the sentence, the presentation about language modeling was so, and then I have mask here, I literally couldn't stay awake. Just for reference, when I put this mask there, what this means is that this is where the model is supposed to fill in the blank, basically. So this is just, mask is like a special token, and we actually just call it in the field like a special token. And yeah, it just represents the fact that the model needs to try and fill that word in. So we have this sentence, the presentation about language modeling was so blank, I literally couldn't stay awake. Now, what our language model will do is it'll take this sequence of tokens as an input, and its output will be a probability distribution over all of the tokens in its vocabulary. So this is just a set, or like five of them that I just randomly kind of came up with. But of course, this vocabulary, the set of tokens that the model can output will be relatively large. It'll be like 50,000 or 100,000 tokens or something. So these can be kind of words, they can be characters. It depends on kind of how your tokenizer is set up. But yeah, the model will output a probability for each of these tokens. So it doesn't think that that if the language model is good, it'll assign low probability to words or tokens that don't seem to kind of fit this sentence really well. But based on the last part of this sentence, I literally couldn't stay awake. This language model might kind of understand that the word boring could go there, or would be pretty reasonable to place there. So yeah, this is kind of the core part of or kind of thing that language models do, is they take text as input and they output this distribution over tokens. Here's another example where instead of the mask token being in the middle of the sentence, the mask is at the end of the sentence. So now, since we don't have the rest of this, I literally couldn't stay awake. Since we just have the presentation was so blank, the model isn't going to really know like what should go there, because it doesn't have any extra information about whether or not the presentation is good or bad or whatever. So it might have kind of an even split between tokens. And again, yeah, keep in mind that this is a very simplified example, right? In reality, there are going to be this is going to be a list of like 50,000 tokens. And so all of the probabilities will be much smaller. But if we just kind of choose like the highest one or something similar to that, then we can kind of see what the model thinks is most likely. So what we could do is we can give it this, and then we can look at the distribution over tokens. And we can see that it has the highest probability is for the word bad. So we could just add the word bad into the sentence and now pass this whole new sentence. So it's most of the same, but it has this extra token added. The presentation was so bad, and then we can add a mask token at the end of this new sentence. So now the model is going to be trying to predict what word should go here. But remember, the model supplied this word itself. So to some extent, it's using its own output as its own input. And you can keep doing this. So maybe the model thought that the word because is likely or high probability. Then we can feed it back in, and we can take the model's output now, which is bad because, and then use that as the new input. And so you can keep doing this, and you can see how you can actually just use this to generate text with a language model, just by putting the mask at the end and then feeding the output back into itself. So this is called like auto-regressive language modeling, where auto is kind of self, and then regressive is like it's kind of this idea of a loop where you're taking its own output and feeding it back into itself. And so if you keep doing this, you can generate text, which is pretty cool. Yeah. Okay. Any questions about that so far? Sweet. So yeah, to kind of recap, a language model gives a probability distribution over tokens. This second point here is something I didn't really talk about, but this distribution is the output of like a large neural network usually. So the input to this network is the text, and then the network outputs this probability distribution. And the way this model is created is by showing it a very large amount of data, and telling it to think that the data that it saw was likely, because the data that it saw was generated by humans, and so we want the model to learn to understand and accurately model human language. Yeah. Just a brief note on what I mean by model. So I've kind of been using it loosely, and it is kind of, I think, an overloaded word to some extent, but sometimes model will refer to the architecture or design that this neural network will have. So you can think about that just like a floor plan or something, just a map of how the text input gets transformed through the model through the network into the output. Sometimes though, it can be referring to the actual values that the network has after it's trained. So the way these models learn is they have like 1 million or 100 million or 1 billion parameters basically that get kind of tweaked as it sees more data, so after the model's trained, these parameters will be what gives the model its ability to understand text. But yeah, before that, the parameters are just randomly initialized. So yeah, that's the basics of language modeling pretty much. What else can you do with language models? I mentioned a couple things at the beginning of the talk. So something like summarization or sentiment analysis, where you're seeing if some piece of text is the person who wrote it, you want to try and assess if they're happy or if it represents something that's angry or sad or something. What's pretty common is to take a language model and then add like a small neural network at the end, and then train that using kind of a standard classification type machine learning objective. The basic idea is that the language model to do the stuff that I was talking about here, like just to predict this token, the only way that it can do that well is if it understands very general information about language. Right? It would be pretty weird if, or it wouldn't really make sense if, you could do this prediction really accurately, but then you just didn't understand anything about language. I don't know if or how that could be possible. So yeah, like these models do learn kind of general and useful information about language, and so you can use that to do other things besides just this kind of prediction, by kind of adding extra modules or like modifying the output slightly. So yeah, this is not, this is very high level. Like it's not I wouldn't expect anyone to like understand, very specifically what I mean by this. But that's kind of the general idea. So yeah, why does language modeling work? Um, the kind of biggest part of this, in my eyes, is the fact that we are able to train large models on a lot of data. So there's this quote by Richard Sutton, who's one of the guys who kind of founded reinforcement learning. He says, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by a large margin. Yeah, the idea is, we take these models, and they're really, really large. And so they take a lot of data to train well because they're so big. And so you train them using like supercomputers, basically, on a giant amount of text. And then this will kind of bake in general understanding of language to these models. So this process is called pre-training. And I'm kind of talking about it just so you can kind of understand the process or flow for how people generally do or use deep learning for NLP. So yeah, these models are pre-trained, by people who have access to a very large amount of compute, and then generally, though, they are available online for download. So you can download them and just and take advantage of that without having to train your own every time, because otherwise it just wouldn't be it wouldn't be tractable to actually do this on your laptop or something. And when I say download these models, I'm talking about downloading the weights or the parameters of these models. Right? You can just look at and understand the architecture, but a model that has 100 million parameters, you just need to download it, and then you can start using it. So yeah, there's this other pretty important kind of general idea called fine tuning. So fine tuning is when you have generally like a large model, but it doesn't work quite as well for your specific problem as you would hope or as you want it to. These during pre-training, the models are being trained on just all kinds of data. So usually it's like a lot of stuff scraped from the internet, and because you need to collect so much, you can't collect only this super specific kind of data. And also it's like more helpful to learn kind of general features by training on a broad kind of diverse data set. So you may have some task that you want to do, and the pre-trained model doesn't perform as well as you would like. So what often happens is you can fine tune it. So basically, you're just training the model. You're just kind of continuing to train the model on your more specific and smaller, generally, data set. The kind of intuition behind why this is useful or done is if you have medical data, for example, right? Let's say it's doctor's notes that have just been typed in to a computer. They're typing language, right? They're just writing some text, and so you want to be able to leverage and use all of the kind of general knowledge that the large pre-trained model has. But doctors use shorthand. They have a kind of different vocabulary. They might just kind of the syntax might be a little bit different because they're focused on something specific. And so it's often useful to fine tune your model on that data, and then it can perform a lot better. To do this though, you still need at least several thousand or tens of thousands of samples. but that's like very, very few compared to the amount that you need for pre-training, which will be like hundreds of millions or billions of tokens or something. Yeah. So if there are questions now, I'm going to go briefly to a kind of interactive, practical example. I actually will send. So I will reconnect here, and I'll send a link to this in the chat. And if you want to kind of follow along with that, you can copy it. I believe you should be able to. So this is Google Colab. It's a super useful tool. Basically, you just have these blocks of text or of code that you can run and change things, and it kind of has saves its state. So it allows you to just do like interactive things and change things around really easily. But yeah, so I'm going to go through a brief couple examples using this NLP framework called Hugging Face. So Hugging Face has a lot of pre-trained models, and they also have models that have already been fine-tuned on specific data sets. In addition, they have a kind of higher level API that you can use if you have some task that is kind of they've already implemented for you. You can just use this high level API, and so I'm gonna just kind of go through this briefly and show it off a little bit. So just run this. So I'm just installing the transformers and the data sets. And so this will take a second and run. But yeah, so I can just talk about this pipeline API. So they have this API called pipeline, and if I hover over it, well, I guess I need to run it first. So what they have is basically they have a lot of just tasks that you can use that they've already implemented. So I'm going to be going through question answering. So if you look here, these are all the different tasks. I don't know if the compression on the video you can see. I think you can. So they have sentiment analysis, entity recognition, question answering, summarization. All these different things. So if you want to use this API to do one of these things, or if you just want to do one of these things in general, I think you totally should just use this, because it's like I don't know, ridiculously simple to do. So you just import it and you create a pipeline with whatever with the task. So in this case, we're going to do question answering. So question answering, the kind of format is it's not general question answering, so you need some context. So and then it'll kind of pull the answer to the question from that context. So here I just wrote this. It says language models take text as input and give probabilities over tokens as outputs. One of the most important and useful language models is called BERT. And then you can see, so all we do is we just pass in any question that we want that we think has an answer in the context, and then it'll output where it thinks the answer is. And so I asked, what do language models do? And the output is take text as input and give probabilities over tokens as output. And that is correct in this context. And then what is an example of a language model? And then it says BERT. So this pipeline thing is just like so easy to use. So if there's one of those kind of tasks that you have, I would definitely recommend using this. The downside to this, though, is that it's not super flexible, right? Unless it is one of the things that they have listed here, you're not going to be able to use it. So I'm just going to kind of go through briefly what they have for just the more general API. So what we're doing is we are downloading from them a pre-trained model. This is just the name of the model that they've trained already. And they have on their website, a big list that you can search through and find different models from. And I'm going to talk a bit after the interactive thing about how you can kind of think about which model is best for your like use case or application. But yeah, so we're going to download a tokenizer. As we talked about earlier, we need to tokenize our text. And then we're downloading a model. You can see here, actually, yeah. So this model is over 1 gigabyte, and so the kind of downside to large language models is that they're large. So they can be kind of slow sometimes, or they can just take up a lot of disk space. But yeah, so now that we have that downloaded, we can see this, and I'm just going to kind of highlight the key lines here because a lot of this is just like formatting stuff. The key parts of this are this line where we tokenize the questions. So for each question, we tokenize it. Then we pass the inputs through the model, the tokens through the model, and the model will output what it has been trained or formatted to output. And and then we take the outputs of the model and we have to convert them back into strings, right? Because the model is going to output some numbers, and so we need to get it back into text. But then we can do that. So if I run this, I just like copy and pasted this from the Wikipedia page for language modeling. But yeah, so you can see that for each of these questions, it just finds the spot in the text that answers that question. So this is just one of the kind of basic applications or use cases of these models. Okay, so going back to this, how do you decide which model you should use? So before I talk about specific models, I just want to kind of talk about the general attributes that you can look at. So one of these, as I mentioned, is the model size. So it's a pretty general rule, and this is related to that quote by Rich Sutton that I mentioned earlier. That bigger models get better results, pretty much. We're not like it. There's a lot of kind of interesting like philosophy about why, and there's some confusion kind of with regards to standard statistical learning theory that seems to kind of contradict or not really explain why this happens. But it's like pretty well empirically validated now that that the larger the model is, basically the more parameters it has, the better its performance can be, as long as it's trained on enough data. The larger the model, the more data it has to be trained on. But of course, the downside to this is that it's much slower. So many large models now, or like the largest models now, can't fit on a single GPU. So you have to distribute them across multiple GPUs, and then you run into how do you update it properly, and all of the kind of challenges that come along with distributed computing. But yeah, I mean they're just slower. They're kind of unwieldy, but they give you the kind of ultimate best results. It's often worth using a smaller model to solve the problem. And there are also a lot of methods that take big models and kind of figure out how to like just make them smaller. So once you've trained a model, there are some ways of pruning it, or kind of distilling it into a smaller model. But yeah, that's kind of one feature. Another is the training objective. So what was it trained to do? And I'm going to talk about this with the two specific examples of models that are coming up. But yeah, this is kind of an important thing to consider. Another thing is was this model already fine tuned for a specific task? So one kind of interesting thing with machine learning in general is that once you've trained a model on a specific task, it kind of gets worse at all the other tasks that it maybe was originally able to do from pre-training. So pre-training, you're just doing this very general language understanding, and so it can the models will be able to kind of do a lot of different tasks. But once you've fine-tuned it on a specific task, it's going to lose its ability to perform on other tasks. And so if you're using a fine-tuned model, you need to be using it for a task that is like close to or exactly the task that the model was fine-tuned to do. But what that means is that you can get better performance, by using a model that has been trained on that specific data set or task compared to just the general pre-trained model's performance. And then you have the model architecture, right? So this is a little bit, this is kind of probably harder to evaluate without, being pretty immersed in the field, I guess. But there are some kind of examples where specific architectures will be well suited for some problems, but not for others. Okay, so I'm going to talk about two models. So the first is called BERT, which I mentioned before. Don't worry about what the acronym actually stands for. Yeah, the acronyms are usually kind of made up just so that they make a nice acronym. I mean, there's some meaning there, but it's not super important. So yeah, BERT is one of the most important models in natural language processing, and the kind of key distinguishing factor or attribute about BERT is how it was trained. So BERT was trained with this example that I showed earlier. So BERT is given samples, which are sentences or pieces of text, and 15% of the tokens for BERT, I think that's what it is, are replaced with this mask token. And BERT's objective is to predict or fill in what that mask token should be. BERT is pretty good at a general range of tasks. It can be, there are a lot, because it was kind of so successful, there have been a lot of modifications and offshoots of BERT, which can be kind of difficult or confusing to go through and figure out exactly how does this, what did they change and why does it actually do better, and what even does it do better on, because sometimes a modified BERT will do better on some tasks and worse on others. So I would say that BERT is kind of just a strong baseline for the most part. I mean, it's not quite state of the art anymore, which is funny because it came out in 2018. And it hasn't been state of the art for a little while, but it's still, the changes are kind of, there's some decreasing marginal return on modifications, and so BERT is a pretty strong baseline in general. But yeah, the key is that they just replace some percentage of these tokens with masks and then try to predict it. So here's the other model that I'll talk about for the last couple of minutes. So this is called GPT-2. GPT-2 is similar to BERT, but the difference is that instead of replacing just random tokens in the sentences, GPT-2 will cut off the end of a sentence and the task will be to predict the very next token. So for this same sentence that we've been using as our example, the for GPT, the way we'll train it is we'll take this sentence and we'll cut off the end of it, and then the task will be to predict this next word here, the blank, the mask token, and so it'll try and predict that, and then regardless of if it gets it right or wrong, if it gets it right, it gets some kind of reward. If it gets it wrong, it gets some like negative reward. But then we add this next word in. We add the true next word in. So we're not doing the autoregressive generation that I was mentioning earlier. We're using the ground truth sentence that we have like scraped from the internet or something, or from a book or whatever. So we replace it with the actual word, and then we feed in these two words, and we ask it to predict what is the third word. And then we feed in the first three words, and we ask it to predict what is the fourth word. So GPT-2 is really, really good at text generation. There's some kind of wild examples. When I first read some of the outputs from GPT-2, I was just very, very shocked at how well it was generating text. But it's not quite as good at the wide spectrum of tasks as BERT. So it doesn't form representations of sentences that have quite as much kind of general information or value. And I kind of want to spend a second and talk about why that is, or what the kind of abstract idea, I guess, for why that is. So if we go back to BERT, if just this mask token, if there's just this one token here that's masked out, BERT has this whole sentence as its input. So it sees the presentation about language modeling was so I literally couldn't stay awake. And the only thing that it doesn't have is this single token here. So it can use the second part of the sentence, the stuff that comes after the mask, to help it predict what this mask token actually is. GPT, on the other hand, can't. GPT only cares about what comes before the mask token, right? It can't even see what comes after, in fact. The way that I kind of think about why this helps BERT understand language more generally is the fact that language doesn't purely work based off of the words that have already been spoken, or the tokens that have already been said. So when I'm speaking right now, I have some kind of broad idea that I'm trying to communicate, and some of that broad idea will be expressed in the second or third or fourth sentence after the sentence I'm literally speaking right now. And what those parts of the idea actually inform what the words I'm using now are. And so GPT can't understand that. It can't, because it isn't able to ever access what comes after in order to predict the current word. Whereas BERT can understand how this second part of the sentence could influence what comes right here. And so this is kind of an abstract view on like why BERT sometimes is more useful. Now, that GPT is like the best model at text generation that anyone has right now. Well, GPT-3 really, which is the like newer version of GPT 2. But yeah, it's pretty interesting to me that you can have a model that is much better at text generation, but it's like worse at these other tasks because of just this way that it's been trained. So yeah, I mean, I hope this was helpful, and that you kind of got a general view on how deep learning is used for natural language processing. And I hope you have fun with this. I would definitely recommend checking out the Hugging Face repo if you want to do some project where you use deep learning for NLP. And yeah, I'm happy to take any questions. I think I don't know how much time exactly we have, but if not, I mean, I would also head out. Yeah, I guess I can just send these here right now. Future applications of NLP I'm super excited about. Yeah, so semantic search is something that I'm really quite excited about. So there's just so much information out there right now, just on Wikipedia, just on the internet, and yeah, being able to just kind of like very broadly express what you're interested in, or kind of what you want to find, and then being able to find like really connected or ideas that kind of offshoot what you're searching for. I'm really excited for that. I just think that can empower learning so much, and help people kind of, yeah, just be able to find information that's much more relevant for themselves. The other thing is text generation. I think that so GPT-3 is like really like even like way better than GPT-2, and so I'm excited to see if they can kind of continue those improvements. The main improvement that they did is they added like 100 times more parameters to the model, and then basically did the same thing. And so, but it performs way better. So I'm pretty excited about that as well. How do we measure performance of an NLP model? Yeah, that's a great question. So there are a couple different ways. So one of these ways is what's called perplexity. It's not super important, but basically what it is just given some sequence of tokens, you can look at the probability that the model gave for each of those tokens. So you can imagine for BERT, just masking out each of those tokens like one by one, for example. And if you kind of add those up, or you add up the probabilities that the model gave for the correct word, for the true word, then you can see if the model thought that the true word was very likely. And if it thought that the true words, that the sum of all of the probabilities for the true words, the ground truth, if those if the model thought that those were very likely, then you have a pretty good language model, because it knows enough to think that to kind of get the answer right for each of those tokens. If it assigns very low probability to the correct word, and it assigns like high probability to some random word that isn't like related, then your model isn't doing as well. So that's one measure, and perplexity is just the mathematical kind of formalization of that idea. But there are plenty of other ways. The standard kind of thing is in machine learning is you have a bunch of different tasks, and you have like a benchmark data set for each of those tasks that some researchers created, and then you can just evaluate the model's performance on that task just with like accuracy or something. So if your task is to let's say your task is to classify a sentence as being like having positive or negative sentiment or something, then you can just look at what how many your model got right, divide that by how many total samples there were, and see the accuracy of your model. So there are kind of for each task there will be some different metric, but the general case is this perplexity metric that I mentioned. That's a good question. The programmers fine tune by adding parameters and changing the underlying model? Yeah, that's also a really good question. Totally. So there are a lot of really interesting ways that you can do this. It can be kind of tricky because when your model's been trained, it's so the way deep learning models work is they have a large number of layers, and each of these layers takes its input, starting from the text, and it kind of transforms it in some way, forms like a representation of it in some like high dimensional vector space, and then it feeds it into the next layer. And so, if you just added parameters in the middle or something, if these parameters weren't trained with the rest of the model, then the layers that come after, let's say you add a new layer right in the middle, the parameters that come after are not going to be expecting these new inputs. So each layer is kind of like expecting some general distribution of inputs, and so if it's like wildly different, then they're just going to be like, whoa, like I haven't seen that before, like what the heck's going on? But there are some kind of clever ways of getting around that, which are actually really cool. There's like someone at the startup I'm working on is working on doing exactly that. So they're called like adapter layers, where you basically like add them into the middle of the model, but you like initialize them in such a way that they give the same output as the previous layer, but then they can kind of be transformed or changed slightly. So yeah, there definitely are ways of doing that. The most common way of fine tuning, though, or actually one like, well, no, I guess that's not really fine tuning. I was going to say like, kind of what I was talking about, where you add a module to the end of the model and just train that. I don't think that would really be considered fine tuning, though, because if you're not changing the underlying weights or the original weights, then I don't think that would be fine tuning. But yeah, people definitely do that. Yeah, of course. So I mean, I guess I can just hang out here for the next couple of minutes in case you think of more questions. Yeah, okay. Where else is deep learning used besides NLP? Ooh, that's a big one. It's used in a lot of places. Maybe the most notable kind of application of deep learning is computer vision. They're called convolutional neural networks. They were created in the 90s, but they became really effective in like the early 2010s, like 2012, pretty much. And you can't really do anything in computer vision without using deep learning models now, just because they're so much more effective than anything else. I mean, the basic idea is like the visual information is just so high dimensional, right? An image that's like 500 by 500 pixels is just that's in like a 2500 dimensional space, right? And that's like just really large. Sorry, 25,000 dimensional space. So you just need to be to be using deep learning for that. Other areas, I mean, there are tons. So actually, one huge news just came out a couple days ago. DeepMind, which is one of the top AI labs, just like last week, I think last Thursday, announced that they solved single single level protein folding using deep learning. So they had been working on this for a while, but they just blew everyone out of the water for figuring out protein folding. So it's basically like taking a sequence. This is actually it is really related to NLP, because they take a sequence of amino acids, and they actually use transformers. So they're using very much the same kinds of model architectures that BERT and GPT use. And then, they do a bunch of other stuff. They have some kind of simulation and some energy based model, and they are able to figure out with very very high accuracy how this set of amino acids will fold itself into a protein. And this is just like so incredibly useful and important, because like protein folding has just been this insanely hard task, and it is like so useful. Proteins are literally what do most of the stuff in our body, right? They are like the engines, or like the building blocks that run like our metabolism and just everything in our bodies, in our cells. And so yeah, being able to the thing is like the previous methods for figuring out how like what the shape of a protein are, you just have to do it experimentally. So you actually have to like use like it takes a long time and is like really expensive. So I think like X-ray crystallography is the main method that's used, and it's just like takes a long time. But yeah, with just this deep learning model, all you have to do is figure out the set of amino acids that makes it up, which is much easier to do, and then you can just pass it through the model and have it predict what the resulting shape of the protein will be, and it'll yeah, you can then just use that to figure out so much in biology. It's like crazy news. I'm super excited about it. But is NLP considered an optimization? Yeah. So you're doing optimization. The way you train it is with optimization. That's a good question. Yeah, I said I kind of mentioned it very loosely here because I was kind of trying to keep it high level. But yeah, so we learn the model by showing it a large amount of data and training it to maximize the likelihood of that data. The way we do that is through optimization. So we use like gradient descent, and those kinds of methods to change the parameters to make the model output a set of probabilities that are closer to the ground truth output. Okay, so I think we are pretty much out of time. It is 6 p.m. Yeah, thanks for coming. This was a pleasure to present, and I hope you got something out of it. And yeah, message me on Twitter or wherever. Send me an email if you have questions or want to talk about NLP. Happy to talk about it anytime. So yeah, thanks for watching. And yeah, check out there are other workshops as well throughout the rest of the night. So bye.